I'm gonna talk about the time series analysis. And the first, let me see. So in the title so far, what we did is, it's a kind of, we did regressions and classifications and dimension reductions, like autoencoders and CNN or any kind of regression problems. And the common things, all these things is based on the snapshot type date. This one is not a formal one. This is the description that I created. It's a snapshot means here, say, for example, for the CNN structures, we take the cat image and do some kind of convolutions, and eventually the output, if there's classification problems, we have the neural net should tell like whether it's the input image is a cat or a dog. But let me ask, so if I put the image like cat first and say, how do I say? Now I want to talk about the sequence. So the single images, that's all the information that we need to tag to classify the input images to, right? But let's think about this example. I'm gonna show you the movie clip. Okay, so let me ask. So just for Gollings, do you think he's doing good or not?
No, he's good.
Huh?
He is good.
Yeah, he's good, right? So let me show the movie clip again, and just think about when the goalie fell down to block the ball. Now, right? So what I'm saying is that, what's the next? This guy, the goalie is what we did is from the, let's say we have some cameras and to perceive the images from environment and for ball as well. And this guy is able to predict, right? That's why it was like when the ball is in the middle, is around here, they decide to flip to block it. This one is not. This one is kind of different applications, like compared to these declassification problems. So the idea is that now sequence matters. Say, suppose like every sec to take the image, suppose, and at like 0 second, the ball was there, and 1 second, and 2 seconds, and 3 seconds, and if you measure it, and at this historical or sequence of informations or sequence of the data set, we are able to predict, where we able to predict, like say at 4 sec, right? I mean, this is too obvious, but now what I'm saying is that sequence matters means now we have to consider time axis as well. Now we have to consider the time axis as well. Steph, can you hear me or no? Yes?
Yes.
So for any other like CNNs or ANNs, did not consider the time axis or time dimensions at all, right? So, and in many, say, any engineered system, suppose like there's some dynamics in it, and we want to know or we want to analyze it, then the most common method or approach that we're gonna take it is like put a lot of sensors, right? And we're gonna store or the sensor readings. For sensor readings, we will do, say, in time, we're gonna sample it like with fixed or constant and constant intervals. So these many kinds of the type of the data will be in the form of a sequence or time series, and we should understand like physics behind. So that's why we need to discuss or talk about the sequence. So what is sequence? I mean, sentence like this morning I took a dog for a walk. This is not like one of the examples of sequence. And in the hospital, is a lot of, you're gonna see a lot of medical signals like this. And speech waveform could be one of them, and a lot of vibrations and like temperature, like average temperature per day, or weather data set, and many of them, or probably I would say most of them, the data, the type that we're gonna see or we're gonna experience every day in the daily basis will be in the form of the sequence or the time series analysis. That's why we need to have another tool to analyze or to understand the sequence data set. That's kind of the motivations. And sequence modeling. And again, what I'm saying is that most of the real world data set will be in the form of time series, I think. And just these are important bit to be considered. Let me see. Like, I mean, this one, you guys can skip it. And use the past and present observations to predict the futures. That will be the main or ultimate goal of when you're talking about the sequence modeling, right? Based on the previous observations or measurement, and you want to know what's going to happen in the near futures, right? So you want to predict the futures based on the past and present, or we can say historical data set. So there will be, yeah. And for deterministic, and probably next one is another one is a stochastic. So deterministic, the time series data set is probably, I think you've seen this kind of things like middle school, high school. Say you have some kind of the sequence of y, and we know that at 0 the value is 1, and at time 1 is the value is half, probably is a quarter, things like that, and we can expect what will be the values for at time 3. What will be the, and probably it will say like that, right? So what we did is you just see the past or historical data set. You kind of, what we did, you model it, but this is very simple enough. But you model it, you learn something, you model the historical patterns from the historical data set to predict the futures. That's basically what you guys did it. And in the closed form proper, you will say like that. I mean, these are the same. And another way that you can represent it, the dynamic sequence or behaviors in the deterministic manner is linear differential equations, difference equations. I mean, these are some of the examples that I want to show with the initial conditions, and say like that. And if with this kind of initial conditions, what I can say is that if y1 is y0, right? And we know that this is 1. So it's half. Y2 is from these equations, we have 1 and we computed it. So it's like squared and things like that. So it's linear difference equation is another type of the models that you can represent deterministic time series data set. And probably you can just add high order the linear difference equations with like that and like this. These are the, but one thing that I want to mention at this is it's all of them are deterministic. So once we have this kind of relationship from either like with the examples and in the closed form, or either in the linear difference equations with the initial conditions, the futures will be determined. Right? There's no noise on uncertainties. There's no room for the uncertainties. On the other hand, stochastic time series data set is a little different. I mean, this will be the, I mean, stochastic is, you can think this is more like probabilistic, or yeah, things like that. Probably like you can think of time series data set with the noise. Probably that's another way that you can think of for the stochastic time series data set. And I mean, as you can see, like there's a lot of like things like that. These will be all can be think of in the form of a stochastic time series data set. And the first thing is non-stationary. Second thing is non-stationary. Stationary means the static characteristic does not change over time. Looks like these at each, like any time, fixed time, all the like mean and variance are pretty much the same. That's the stationary things. You can think of, say, you have any mechanical systems and it's operating in a normal conditions. Then if you put the sensors, the values probably the sensor readings probably it looks like that, right? A lot of noise added, but in overall the signals will be the stationary. On the other hand, for non-stationary means like mean and the variance is gonna be change over time, like this. Looks like the mean is, and probably like I would say like this. The variance probably will be this. We have high variance, and on other occasions, probably another time, the variance the value is gonna be very small. So it's a non-stationary. Okay. And how you deal with the non-stationary? If let's have linear trend, probably you say, let me see. Okay, why? If this is the blue one, you can model it as a say, right? And noise on it, edit it. Probably noise will be, you're gonna assume that it's Gaussian, which makes sense. And you need to find out A and B. This is same as linear regression problem. But here, what we need is, in given this kind of non-stationary stochastic time series data set, you have to assume that it is linear trend. This one is the structure, you have to assume it. And if you have a nonlinear trend, probably is, maybe you can think of linear, polynomial functions or the exponential functions, right? So in that case, let me see, like that. T, like, I don't know what, like say, And these, the unknown parameters that we need to fit the models. But in the structure of models, that's something that you have to assume it. Say for this kind of nonlinear regressions. I mean, this one is one of the possible way. Another way is probably like t square and t quadratic cube, things like that. Also, you have to decide the degree of the polynomials as well. And this one is nonlinear regression problem. Another famous or is the thing that you often see in the non-stationary time series data set is seasonal trend. Maybe like say in we have 7 weeks, right? It's some patterns are gonna be repeated, or you have a month, or you have like the spring, summer, and like all 12 months, every year you're gonna see like some repeated the patterns or periodic signals like this. Then to decompose that kind of thing, you probably know that is all the periodic signals you can decompose it. Sine and cosines basically it's a sinusoidal signals. I mean this is FF. I mean Fourier series or Fourier transform. So it's sine like omega t plus cosine omega t, like gamma 1 and gamma 2, things like that. Some kind of constant. So now from the data set, you have to estimate these kind of unknown parameters, but everything is a parametric problem. So if we sum up how to deal with the non-stationaries is we need to assume the model first. So like that. We don't know whether it has a linear trend inside non-stationaries, and probably nonlinear behaviors and the periodic behaviors, things like that. And basically, this one is parametric and fittings. And this will be is a non-noise, and hoping that this one will be Gaussian. Right? If this one is, if it's not a Gaussian distributed, that means somehow we fail to find or fit the good models. So that's see the indicator. So that's kind of general, like traditional way of thinking the time series data set. Another way is the Markov process. I'm not sure whether you guys are familiar with the Markov chain or Markov process, but I'm gonna give you some kind of brief introduction on these topics because this one is also related to the sequence. So sequential process. Again, the most classifiers ignores the sequential aspect of the data set. Right? It's same as it's opposite way of snapshot type data. So how do you take into account for sequential aspect of the data set? That's the key in here. So for that in here is in the Markov process. Let's think about what kind of system or what kind of assumptions that we're gonna make. So we're gonna consider the systems which that occupy one of the n discrete states or categories. So our systems can have only discrete number of states. Yeah. I mean, this is why it's not a continuous. This is just kind of how the Markov process. So in the Markov channel process, we're gonna assume that n discrete state. That's right. And we are interested in the stochastic systems in which the state evolves in have some randomness on it. Okay. And suppose we have this kind of sequence like Q0 and Q1 and Q2 and QT. Each time does have one of the n different discrete states. And I want to compute the probability of this. Say we have this kind of sequence over there from time from 0 to capital T. So we observe or measure some kind of the sequence. We measure the sequence. I want to calculate the probability of having that kind of sequence. There will be I'm not sure whether you took the probabilities, the course or not. This one is the conditional distribution. So at the first time, at time 0, we have to have Q naught, right? And in next time index, we observe the Q of 1. That means we got Q1 given this is conditional probabilities. We have to have that. So up to here is we have Q naught and Q1. And to have in the next probabilities that we need to multiply is given having the sequence of Q naught and Q1, now I observe Q of 2. That's the probabilities. But we're gonna keep going. But the problem is it's almost impossible to compute. It's almost impossible to compute. That's the big issues. So the Markov chain there's some Markovian properties, which is the assumption that we're gonna have in the systems. Basically, we want to simplify because in here is this one is the probability that we want to compute in the conditional probability they want to compute is almost impossible. So the Markovian property is like that. This means we got these kind of the sequence, given that I want to predict what kind of the values in the next step. But we assume that this one. So that means in order to predict all the information that we need is this one. We don't need any other previous the observations at all. I mean, whether this is true or not, it doesn't matter. It's the assumptions that we're gonna make for the Markov process. Okay. So now it's tractable in computation of joint distributions. Why? Because this one was but as you can, this one is this. Now we don't need this. Now we don't need these two. And this kind, the conditional probabilities, probably we can compute. So the future is independent of the past given present. That means the future given present. This is present, and the past probably like independent. I mean, okay, so let me see, like, so we had rain and snow and sunny day and sunny day and sunny day and rain, and yesterday was a snow, and what kind of weather that you're going to have for, I mean, today it's snowing, suppose, and what will be the weather for the tomorrow, all right? And this is kind of like daily problems, and we're always talking about the weathers, but so you can think of as that this is also sequencing problems, and we can have all the historical data set for weather informations, but in the Markovian properties, saying that in order to predict tomorrow's weathers, all the information that we need is today's weather. Of course, it does not make sense, but this is the Markovian properties and assumptions, and in order to make this, the model it's simpler, right? Now I can define another. So one is the state transition matrix. You guys might wonder what it is. So for Markov state S, in the next state is Fs prime. So now we're going to make transitions between. So say at time t, the state is S and t plus 1. Then we have, this is the probabilities, because we're trying to deal with the randomness in it. So for P, this means from S1, this P of 1 means from S1 to S1. That's the probability. We have all the probabilities here in element in the state transition matrix. Probably this will be much easier, make it to understand easier. Suppose we have only 3 states, like that. And now in this state, so now is, let me see. This means suppose you are in this state, the first state, then in the next state, you're gonna make transitions to another state, in this case in S3, in third state with 1 probability. Right? And now I'm here, say we are here, then now I have now 2 chances to, I can visit S of 1 or S of 2, but now I have 1/3 and 2/3 probabilities. So now I assign different probabilities. So from here to state, if I'm here, now I can have, if you are here, you have 2 chances. The one is you can jump to the first state, or you decide to stay at the same state with half and half probabilities, right? Then, as you can see here, S1, S2, S3, from, here is from S1, S2, S3, S2, right? So you have, if you are in S1, you have 1 probabilities to visit or to make transitions to a third state for sure. And if you're in S2, you have like that. And if S3, you have this kind of. So that's the P, which is state transitions in the matrix. Now you from the name, you're hoping you understand everything. It's a state, but it's a transitions, because we put it in the matrix form. That's and one of this is the why I did discuss and explain what's the Markovian chains for the sequence, the sequence or the time series data set. Say that suppose you start from the first state, so everything is here. So you are here, and then you jump to the state here. Then in the next time, probably you can visit over there, and you will stay there in the next, and you that's the sequence that I generated, right? That's the thing that you can generate. Another sequence that you can think of, again, is from starting from here. You have to go there, and then visit here. I'm going back there. That's the second, the sequence. So you have episode, it's a sampled episode. another way is that over here and jump there, jump to and stay there and stay there. That's the sequence that I generated. So the Markov chain let us generate the passive stochastic sequence. So it's a passive and it's a stochastic. We have a lot of, see, as you can see, so you can generate different episode or different sequence with some kind of probabilities or based on the randomness. But the reason why I say it's passive is there's no control on it. It's gonna just follow the state there, and based on this probability, they're gonna decide in which state that you're going to visit it, right? So say passive and stochastic. So that's the reason that this Markov process or chain is one of the way that we can generate the sequence. That's the reason that, and the key thing is, again, we can generate the sequence which is stochastic. All the information, the stochastic, the state transition matrix contains all the necessary information for stochastic behaviors or stochastic sequence. Now I'm going to move on or make the advance to the, is from the Markov, we have now is at hidden Markov models. How do I say? This one is in, like, how do I say? I'm for the sequence, I'm gonna explain the recurrent neural net probably next time. But the key idea is starting from the hidden Markov models. The key ideas. So what is key ideas? So it's a discrete state space models and state representations. What I'm saying is that, say, how do I say? The assumption over there for the to deal with or to understand the sequence data set is we can observe or we can measure something that's affected by the true state. That's something, how do I say? This is natural way of thinking. Let me see. I mean, let's think about the temperature of me. So I'm gonna measure the temperature like every hour. So there will be like the temperature, things like that, the trend. That's the sequence data set. So that's something that we can, that's the measurable, the data points and observations, I would say Y. But temperature is temperature, does not tell anything. Suppose, say, the goal is that I want to know the condition of my health. Maybe say like health conditions of myself. Then the state is probably we don't know what it is, whether it's observable or not, and we don't know whether it's measurable or not. But that's something the state X, and which is the true state, which represent the health condition of myself. But that's something we cannot directly measure it. But the health of conditions we're gonna affect the temperature of myself. So that's the configuration, the scheme of the. So here this is the state over there. The state, I'm gonna assume that it's followed. State can be represented by the Markov models, and each state we're gonna emit the observable the sequence or data. That's the idea of hidden Markov models. So it's the Markov models, but the hidden means that the name is coming from the fact that is the true state is hidden, or true state is unobservable. That's what. Right? That's the idea of hidden Markov models. So true state follows the Markov chain. The observations or the measurements can be emitted from the state, and YT is noisy, and it only depends on the current state. Okay. And what we want to know is that it's a sequence of observations going to be generated. That's the only thing that we can see. And out of this, from the sequence of observations, the question is we want to estimate the current state, because that's so from say the sequence of the temperature, I want to know the health condition of myself as a form of conditional probabilities. That's the key, the framework for the hidden Markov models. And the key idea is that the true informations are something is represented by states, but that's true values, true information that we want to know. But that's something probably it's abstract or it's unobservable. So the idea is that instead of just having direct access to the state, instead of we can measure or we can see the observations. So from the sequence of observations, how we estimate or infer the true current state, there will be the framework for the hidden Markov model. Okay. And the last topic will be the Kalman filters. And I'm not sure whether you guys may heard of the Kalman filters or not, but this one is something that is developed from the control theory. And so again, because this is very, very high level of explanations or brief explanations. And again, you don't need to know, but the key thing is that, let me explain this. The Kalman filter it's a linear dynamical systems of motions. We have that. Say, let me see. How do I say? So in this, if that's the state of my systems, can be represented by like this kind of linear models. Suppose the matrix of A and B and C, and the observations Z it's a function of state, yeah? And here it's a linear dynamics. And this one is the observations or output is only function of state. And this one is from that is the idea is that okay, if we know the state in the previous state, based on this information, we can predict the true state, right? And at time t, at the current time, we're gonna measure the observations. Now, based on this information, we can update it. We can have better estimation on the current true state. That's the idea of Kalman filters. Let me see. Okay, and I'm gonna show you this. I'm not sure whether you, let me see. Let me share the sound. I'm gonna show you the movie clip.
There's a really nice little graphical illustration of tracking with Kalman filters. So let's suppose we have some current estimate of where we think things are, right? And that's what's represented by this little circle here in the XY plane. Our prediction shifts and grows, and that's why the size, if you will, and you can think of this as being a single, say, some number of standard deviations of uncertainty. So our uncertainty matrix got significantly bigger, and the mean may have shifted as well as also, so that's our prediction. We then take a measurement, and you'll notice that the measurement here is offset a little bit. I mean, and it happens, you know, its mean is right in the middle, and it's actually tighter. So it actually has a tighter covariance than the prediction, okay? But the thing that's important to realize is the correction has a tighter covariance than either one of them. So you'll see that the mean of the final correction is somewhere between the mean of the measurement and the mean of the prediction. Remember, it's going to be a weighting between them. And also notice that the covariance of the final corrected estimate is smaller than either of the two, all right? And this might seem a little weird when you look just at, say, the covariance of the measurement and the covariance of the prediction, because they're both pretty big. And you might ask, how is it that the covariance goes down even tighter than the measurement? And again, the answer is information can only reduce your uncertainty. So whether you think of as measurement as reducing your uncertainty about the prediction, or the prediction is reducing the uncertainty about the measurement, what that means is your final covariance will be less. You'd be amazed at the number of PhD qualifying students who, when asked that question standing in front of the board, kind of flump through it. So if you're thinking about doing a PhD, and I'm going to be on your qualifying committee, and you're doing something in robotics, get to know and love your Kalman filters.
Okay, so that's the movies. Probably you guys can click this YouTube and you guys can watch it again at home. So the idea is that, okay, let me go back to, we had I explained what time series data set, and there's some, and have hidden Markov models, and this one is, another one is Kalman filters. For hidden Markov model is that this is the basic assumptions, but the problem of this case, we have to know the P matrix in advance. And we have to define the state as well. But the only thing that we have is a sequence of the observations. That's the only thing that we have. That's the weakness of hidden Markov models. We have to know a lot. For Kalman filters, we have to know this kind of the dynamic equations in advance. That means we have to know A and B and C matrix and state as well. Okay. So again, the message that I want to make here is that hidden Markov models, Kalman filter, those things are beautiful, right? But thing is that in order to make those kind of things work, we have to know a lot of things. We have to know what kind of state that we need to represent the models, and what kind of the linear models like A, B, C, D, and what kind of the state transition, the probability matrix, things like that. That's the drawback of the conventional way, or the traditional approaches to analyze the time series data set. But for the, like, again, this, I mean, the hidden Markov Kalman filter is kind of the machine learning. We have to know the feature. We have to know. But deep learning, again, is we're gonna ask RNN models to extract the features from the sequence of Y's, like that. So we're gonna ask in deep learning models, from the sequence of the observations, you want to estimate it A and B and C and X, everything. That's the beauty of the Kalman, the RNN models.